If the last lecture could be called Fun with Partial Differentials, this lecture can be called More Fun with Partial Differentials. What we're going to derive here is a set of equations called the Maxwell equations. This Maxwell is the same as the Maxwell who derived the Maxwell equations, which explain propagation of light. All right. Now remember from last lecture, I hope I convinced you that the state functions U, H, internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy are state functions of two variables. And again, we got that considering only PV work. All right. So for that case, it's only there are only two variables. Now, what I'd like to convince you of here is that, say we take U, which we said was a function of the natural variables S and V. Suppose we take the derivative of U with respect to that first one, S, at constant volume, and whatever that is, take this with respect to the second variable, how V, this would be a constant S. That is equal to how U changes with that second variable, V, at constant S, and then how that quantity changes with S at constant V. That is to say, it doesn't really matter whether you take the derivative of the first and then of the second, or take it of the second first and then take it derivative of the first variable. Those quantities are equal. And the reason is that these are state variable or state functions. So U is a state function, which means that du is independent of path. All right, it's independent of path. So you want to get someplace in three-dimensional space. These is the x and a y, and u is a z. So it doesn't matter whether you travel along the s-axis and then travel up the v-axis, or travel up the v-axis and then travel along the s-axis. It doesn't matter how you get from some initial to final state or some infinitesimal change. You can either go along one axis and then the other, or along the other and then the one axis. It's because state functions are independent of path. And that's what Maxwell realized. Oh, these are state functions, and therefore we can write something like this. All right, well, let me reproduce that over here. So how U changes with that first variable, S, at constant second variable, and how that quantity changes with the second variable at a constant S. And we're just going to switch the order of differentiation. We're going to take derivative of V first at constant S, and then take the derivative with respect to S at constant V. Remember from the last lecture, we know how U changes with S at constant V is. How U changes with S at constant V is temperature. So that is temperature. And how U changes with V at constant S is minus pressure. Okay, minus pressure. That's what that is. All right, so what Maxwell realized, how temperature changes with volume at constant S. We just substitute in this expression for temperature, so we're taking the derivative with respect to temperature, or derivative of temperature with respect to volume. That is equal to, put that minus sign out there, how pressure changes with entropy at constant volume. This is a Maxwell relation, and that's something you wouldn't think off firsthand. Why is this useful? Well, for instance, if you want to know how pressure changes with entropy, it's kind of hard to change the entropy, but that's equal to the minus of how temperature changes with volume at constant entropy. So that's kind of an interesting relation. Let's do the same kind of thing for the other three functions. We said that H, enthalpy, is a function of S and P, and entropy and pressure. So it doesn't matter how we take the derivative. We take the derivative of F with respect to that first one, S, at constant P, and then take the derivative with respect to P at constant S. That is equal to how take the derivative with respect to the second variable at constant first variable, and then the derivative with respect to S at constant P. All right, what is this one? How H changes with S at constant P. How H changes with S at constant P is temperature, and how H changes with P at constant S is volume. That's volume. So here's another Maxwell relation. How temperature changes with pressure at constant entropy is equal to how volume changes with entropy at constant pressure. That's kind of cool. Another Maxwell relation. Let's do the third one. We had Helmholtz free energy A. We said that was a function of temperature and volume. Therefore, how A changes with temperature at constant volume, and then take the derivative with respect to volume at constant temperature, that is equal to how A changes with volume at constant temperature, and then how that changes with temperature at constant volume. All right, let's take a gander, see what these things are. How A changes with temperature at constant volume. How A changes with temperature is minus S. Oh, cool, minus S. And how A changes with volume. Well, you know, we could sort of figure this out. What's the conjugate variable for a volume? It's pressure. So here we're down here with a minus sign. So minus pressure, minus S minus P. So another Maxwell relation is how how entropy changes with volume at constant temperature is minus how pressure changes with temperature at constant volume, constant temperature. Let's put a plus sign just to make that easy. A third Maxwell relation, that's kind of cool. And finally, let's use the Gibbs free energy G. We said that was a function of pressure and temperature. So I'll do it one more time. You're probably tired of this, but just one more time. How G changes with pressure at constant temperature, and take the partial derivative of that with respect to temperature at constant pressure. That's how G changes with temperature at constant pressure, and the derivative of that with respect to pressure at constant temperature. What do you think this is, and what do you think this is? Well, that's probably related to volume. Yeah, there it is. How G changes with pressure at constant temperature is volume. And how G changes with this is volume. Getting ahead of myself, getting all excited here. I was right the first time. Good thing I didn't change the eraser. All right, how G changes with pressure. Pressure will be volume. And how G changes with temperature at constant pressure, minus S. So we get the Maxwell relation. How V changes with temperature at constant pressure is minus how S changes with pressure at constant temperature. Look at that, a fourth Maxwell relation. All right, so you see how those come about. The key point, it rests on the fact that these functions are state functions. And state functions, when you go from initial to final, or when you go infinitesimally, they're independent of paths. So you can go along the first variable and the second, or go along the second then the first, you get the same thing. All right, so where are we here? Here's the lecture. Yes, so this is what we just did. And here's a summary table, nice summary table of the Maxwell relationships. All right, let's do an example where that comes in handy. This is a show that problem, and you'll probably encounter one on the first exam where you're given some equation. You have to show that the equation is true or derived from something or other. So show that for an ideal gas, this equation is true. And we're going to use a Maxwell relation in the solution to this problem. And this is problem 430 of Ball. Okay. Oops. Okay. So let's start, excuse me, let's start by writing down that equation. Yeah, I might as well write down the equation. So here's the equation we want to show is correct. Cp minus how U changes with temperature at constant pressure minus how H changes with pressure at constant entropy, and then how P changes with temperature at constant volume. We want to show that is equal to 0. Okay, remember that Cp, we'll change that, is how H changes with temperature at constant pressure. That's our definition of Cp. Okay, so let's put that in there. So now our equation is how H changes with temperature at constant pressure minus how U changes with temperature at constant pressure minus how H changes with pressure at constant entropy times how pressure changes with temperature at constant volume. That's equal to 0. All right, here we have an H, and here we have a U, and we know a relationship between H and U. In fact, we know that H is defined as U plus PV, so that how H changes with temperature at constant pressure is how U changes with this constant pressure with respect to temperature times constant pressure plus how we use this PV changes with temperature at constant pressure. So we just took the derivative of this equation with respect to temperature at constant pressure. Let's now plug that in there. So we'll substitute this term for that, and we end up with how U changes with temperature at constant pressure plus how PV changes with temperature at constant pressure. And then we'll write the rest of that equation. So we substitute in there, and here's the rest of that. Oh, look, this is going to happen. How U changes with temperature at constant pressure. Well, that's kind of cool. It's going to cancel out there. Minus how H changes with pressure at constant entropy, and how P changes with T at constant volume. We'll show that is equal to 0. All right, so we're on our way. We got two things to get rid of, or we got rid of two things. So we'll just rewrite this equation: how PV changes with temperature at constant pressure minus how H changes with pressure at constant entropy, how P changes with T at constant volume is equal to 0. Aha! This looks like we can substitute something in here. Let's see, how H changes with pressure at constant entropy. What do you think that is? Probably related to something to volume, because that's what's associated with P. But let's go up here and let's see if we can figure that out. How H changes with pressure at constant entropy is indeed volume. All right, so that's volume. So we now rewrite this as how PV changes with temperature at constant pressure minus V, how pressure changes with temperature at constant volume. That's equal to 0. And let's rewrite this in anticipation of where we're going. How PV changes with temperature at constant pressure minus how, see, V is a constant, so you can pull that into the derivative, how PV changes with temperature at constant volume equal to 0. So I think this term is equal to that term, and therefore when you subtract the two, you get 0. But just let's show that explicitly. So now we have an ideal gas So we know that PV is equal to nRT. So dPV is equal to d nRT. Okay, so if we go back, we can just substitute in for PV nRT. So this is how nRT changes with, what was that first one? T at constant pressure minus how, again, we're substituting in for PV. I'm just going to put PV in there, minus how nRT changes with T at constant volume. Is that equal to 0? Well, let's see. N and R are constant. The derivative of T with respect to T is just 1. And it doesn't matter whether it's P. So this is just equal to NR. Same way here. The derivative with respect to T, N and R constant. You pull that off. The derivative of T with respect to T is 1. Doesn't matter if it's constant volume. NR is 0. So therefore we had QED. Whatever that means. That's what the mathematicians use when they've shown something. Okay, so that's an example. Actually, we did not use a Maxwell relation to solve this. The key realization here was from the previous lecture that how H changes with P at constant S is just volume. All right, so that's it for Maxwell relations. They're handy. You might keep in mind what these are. And again, you don't have to memorize these, although they're kind of easy to derive. You don't have to memorize these because the exams are open book and open notes, and any notes you have on your computer and so on, so you just have to know how to reference it. All right, that's it for Maxwell relations.